Hello, and welcome to Field Measurements of Precipitation and Snow. These are just a few slides to get you thinking about different ways to measure snowpack and precipitation in the mountains. I'm Dr. Nolin in the Department of Geography. Glad to be here for a guest lecture, and I'm looking forward to seeing you on the quad where I can show you some cool instrumentation. Just a outline, I'm going to talk about different kinds of precip measurements, how hard it is to measure snow using standard gauges, different ways of measuring this important quantity called snow water equivalent, measurements from automated sites called SnowTel, and different ways of measuring snow along transects, which we call snow courses, and snow pits, and then of course the measurements that I'll be demoing on the quad in class tomorrow. Okay, precip gauges. Precipitation is a really fundamental input that we need when we're modeling snowpack. We can't measure snow all over the place, and we certainly can't measure it at the critical scales of the process, so a lot of times we're going to model that. But in order to get the model running, you have to drive the model, or we call it forcing data. So meteorologic data such as precipitation is pretty fundamental. But we always want to try to figure out, okay, is our precipitation estimate true? What is the ground truth? But we don't actually have great precip data for a lot of places, especially in the mountains. It's really, really hard to get good precipitation data from mountain regions. It's just too remote and too hard to maintain a lot of these stations. A lot of times what we do is we won't we won't be using the NIST, National Institute of Standards and Technology primary standard, but you'll use what's called a secondary standard, and even that is far more involved than what we typically see on stations where we're measuring precipitation. Here's an example of this double fence intercomparison reference, DFIR. It's an octagonally shaped double fence shield used to basically reduce the turbulence around a gauge. The gauge is actually the sort of metal thing with a sort of a hole where ideally you'd get the snowflakes and raindrops to go down there. But the problem is that any turbulence, any small amount of turbulence, really kind of steers the snowflakes away. So it's really hard to measure snow in one of these gauges, but this is sort of one of the best ways you can do it. But there's always some level of undercatch that's happening. Here's some of those gauges that are oftentimes used, and the one on the upper left is what we often see. It's a standard gauge with a thing that looks sort of like a metal hula skirt around it. An altar shield is what it's called. And these are sort of metal things that kind of move around and break down the turbulence a little bit. The Knifer gauge, that sort of spaceship looking thing, is often used in Canada. The Tretyakov gauge down there in the bottom is what you'll often see and collected with data from Russia. Most of these gauges include some sort of antifreeze, a glycol solution of some sort, topped with a thin film of oil. And the reason you have both of those in there is the glycol solution or antifreeze keeps the moisture from refreezing. So if you get rain in there, it's not going to refreeze. And then the thin film of the oil on the surface keeps it from evaporating. Snow water equivalent. This is if you melted the snowpack instantaneously, how much liquid water, what is the depth of liquid water that would turn into? So we have the snow water equivalent, SWE, and this is kind of the holy grail for a lot of our snow measurements. We really want to know what this is, and it's actually incredibly hard to measure. It's simply the density of snow divided by the density of water times the snow depth itself. Now, if we can assume the density of liquid water is about 1,000 kilograms per cubic meter, and in fact, it's a little bit different depending on temperature, but then we can sort of just say, all right, it's the density of snow times the depth of snow. But the density units cancel out, and you end up with depth units. So SWE is measured in units of liquid water equivalent. But how do you actually measure this? Well, here's a big deep snow pit in which we know the depth. You've got a big long ruler there. You can see along the smooth face of the snow pit, and you can see what looks like all these little cuts in the snow pit, and those are sort of wedge-shaped volumes of snow that have been extracted from the snowpack using a cutter, and you'll see that in the field demo tomorrow. And then you weigh that known volume of snow. So you know the volume of the snow, and you know the weight of the snow, and that can be translated into the snow water equivalent very, very readily. So we can compute the snow water equivalent for each layer in the snowpack, and a lot of times we take replicates, which is why you have multiple measurements going across in each 10 centimeter depth. And so then if you know the snow water equivalent for each, in this case, 10 centimeter layer, add them all up, and that's the snow water equivalent of the entire snowpack. So we call this the snow pit method. The second method is the gravimetric method, and this is the one that James Church actually invented. James Church is the sort of the original father of snow surveying. He was a classics and history professor here at UNR, and he invented what was called the Mount Rose sampler, which we still widely use today. So basically, again, we take a known volume of snow, and in this case, it's like coring the snowpack with this long aluminum tube that's specially machined with a fixed volume, and you insert it vertically all the way down the snowpack until it reaches the soil. You give it a twist, you pull it out, and you weigh it. And you've already weighed the tube without snow in it, and then you weigh the tube with the snow in it. Then you have a known volume of snow in the tube, and you can convert that to snow water equivalent. And here's an example of weighing the tube. We use a spring scale. Another way of measuring snow water equivalents is using a pressure transducer and literally weighing the mass of snow that's lying on top of this flat surface. In some cases, it's a surface sort of like a bunch of steel plates, like kind of shown here in the diagram. And those, it's inserted, it's kind of installed in the ground before it snows, and you have this electronic pressure transducer that's hooked up to power, and that when snow falls on these steel plates, it registers a voltage, and then that pressure transducer is calibrated to turn that voltage into a snow water equivalent measurement. And essentially it's the mass of snow, the weight of the snow on that steel surface produces a voltage and returns the weight of the snowpack. Another type of snow Okay, a snow course is simply a transect where they make repeat measurements along that transect, they being members of the Natural Resources Conservation Service. Many of the snowtel sites that I just mentioned are located along what used to be snow courses, and then the snowtel sites give automated measurements. The snow courses are manual, and the snow courses are really only visited once a month. Many of them have been abandoned in favor of these automated, much more higher frequency measurements at the snowtel sites. But the nice thing about snow courses is that they measure like through a meadow and through the trees, and so you're capturing a lot more of that variability. And they're typically like anywhere from 3/4 to a full kilometer long, marked with points along these intervals, depending on the terrain. So you're really sampling across the terrain, and it can be perhaps a better way to characterize the snow accumulation and melt processes. Here's an example from one of my snow hydrology classes of students probing the snowpack and making deep measurements of snow depth along a transect. You can see the measuring tape along the bottom there, and they're snowshoeing along through a burned forest. So we would oftentimes, in my students' work, make measurements in burned forests, in meadows, and in dense forest canopies, just to get a whole wide variability of snow accumulation and melt processes. Here's an example of a snowtel site with a lot of different things that are labeled here. You can see the snow pillow there on the ground. You can see a marker there that might be indicating snow depth. If someone were to snowshoe up to that site, they can see what that snow depth looks like. You can see the snowtel shelter where the data loggers are kept. There's solar panels up there which power everything in the wintertime and throughout the summer. You might have a snow depth sensor, which is an acoustic sensor, kind of a pinger in a sense. It sends out an acoustic signal, and then the amount of time it takes for that signal to get back up to the sensor tells you the distance from the sensor to the surface of the snowpack. It's kind of the way that some cameras work. There are also temperature sensors there, and occasionally there are additional sensors like relative humidity and incoming solar radiation. You can also see that precipitation gauge back there, the thing that looks like a rocket launcher with the altar shield around the top of it. But there are loads more new instruments these days, and a few that you'll see in the field day just coming up tomorrow is a field spectrometer that we use to measure the albedo, which is the reflectivity of the snow. We measure this in lots and lots of different wavelengths because snow is actually not as white as we think it is. If we had eyes that were as sensitive as my field spectrometer, we'd see that it's blue, and we'd see that it's really highly variable in the short wave infrared, the near infrared wavelengths, where it can be quite dark, in fact. And as you get to the much longer wavelengths, snow is really one of the blackest substances on the surface of the Earth. The other thing we can use is a really cool kind of snow depth probe that is digital. It's GPS enabled. It records the location in terms of X, Y, and Z coordinates using a mini data logger, and it uses a really interesting way of using magnetic fields to measure the distance from the tip of the probe to the top of the snowpack surface, and it's really fast, a really great way of doing it. We also have an electronic liquid water sensor that we might use in a snow pit to determine whether a layer in the snowpack contains liquid water, if so, how much, because one of the other important quantities that we want to know about snow is it melting? And if it is melting, how much liquid water is in the snowpack? How long is it going to take that liquid water to depart the snowpack and maybe get into the soil and the streams and eventually our reservoirs, because river forecasting is a really critical part of snow hydrology. So I look forward to seeing you tomorrow, and I hope this short slideshow is helpful. Thanks. Bye.